Welcome to the office. We want to take a look at cyclic groups today, and we want to classify them. And it works out to be that every cyclic group is either isomorphic to Z itself or is isomorphic to Zn for some n. And that is precisely the statement of the theorem that we want to consider. So let's take a look at our notes briefly. Now, the proof for this theorem is a little bit longer. It isn't that bad. It's actually pretty straightforward to walk through, but it is a little bit time consuming. So I just want to present the idea. But again, our theorem states that for a cyclic group with some generator, the group is either isomorphic to Z in the case that the order of G is infinite, or if the order of G is finite, then G itself is actually isomorphic to Z sub n. Okay, so if you need to recall what Z sub n is, right? Z sub 3, for example, the set itself is of the elements 0, 1, 2, and then we're working with modular arithmetic under addition, right? Addition modulo 3 there. So that's what it's referring to with this group, and then addition under all integers here. Essentially, what we're going to do is we're going to define an isomorphism. So we want to define phi from G to the integers, right, maybe subscript n there, by phi of a to the I, don't want n takes on a specific value, but phi of a to the I is equal to I itself. Now, normally you would probably think of it as, well, define phi of I as a to the I and just go from Z to G, which would be fine as well for the most part. I'm not sure why they don't go about it that way in the book, but I think the concern is more about whether or not the function phi is well defined, which is of great interest as we approach the proof from the textbook. So again, I'm kind of explaining, giving the idea of what they do there. In order for a function to be well defined, essentially we just have to make sure that it satisfies the definition of a function. Every input only has one associated output. So with my input of a to the I, right, this is just an element of G. I need to be sure that this only has one possible output. Now, if we have that a to the m is never the identity, that is, every integer that I put into the exponent gives me a new element of G. Okay, I never get the identity, then I never end, right? I'm getting that infinite order there. So I'm going to be isomorphic to all of Z. So if that's the case, then we can recognize that it's well defined because every value of Z that I plug in for I gives me a different result, right? A to the third is different from a to the fifth, always, as long as we never have the identity. And the reason we can recognize that is because if we did end up with with two of the same output, then when we consider inverses, we would end up with essentially something that gives us the identity for a positive integer power. Okay, positive, so not zero specifically. So it's well defined, and then of course it's pretty clear that it's one-to-one. It should be pretty clear that it's onto, and then showing that it actually holds the property, the homomorphism property is pretty straightforward. Okay, take a look at the book for that. So again, the hard part of this is just verifying or justifying why the function is well defined. So once we get to here, we do get, we say, all right, well, what about the finite case where G is like this, right? Z3, or right, something that we'll show is isomorphic to Z3. But when that's the case, we end up with a to some power is the identity. Okay, that's fine, right? Here, expressing it as exponents while also talking about under addition is a little bit weird. So we're using multiplication for the implied operation within G, whereas we're using addition here in Z. So again, just carefully think through what group we're in for the appropriate notation. but 1 is the generator for Z3, and A is the generator for G. Under that recognition, 1 plus 1 gives us 2, 2 plus 1 gives us 3, which is equivalent to 0 mod 3. So we can see that it walks through all of them. Of course, if I were to do 1 plus 1 plus 1 plus 1, I can do more than that, but it's going to bring me back inside the set Z3 once I consider the modulo. In the same way, there is a smallest number n that's going to take the generator A and create E. A to the n is the identity. When we use that, we can essentially what happens is we apply the so we're going to apply the division algorithm. There we go. That's what I was looking for, is identify quotient remainder. And what that will do for us is that we're right, a to the big number is equal to a to the r, whatever that remainder is. Because a to the m can be written as a to the, we'll call it nq plus r by the division algorithm. Well, a to the q raised to the n is just the identity, so you're just left with a to the r. So you can always bring it back inside. So if we then are working into modulo n, then we'd never be outside of this, and everything can be identified by that. So then we only have to worry about the numbers 0 through n, or right, 0 through n minus 1. But that makes it well defined for us, because every time I plug in one of those numbers, 0 through n minus 1, I do get something different. Otherwise, it would contradict the smallest nature of n itself, whatever that was chosen for that. So it's well defined, and then clearly it will, since the group is order n, then it will be 1-to-1, it will be onto, and then the homomorphism property is going to again be satisfied, and you can look at the book for that. It's the same thing that we've been using, nothing too different. So again, those are our two cases. The case where the group is isomorphic to all of Z, or the group is isomorphic to Z sub n. But the point is, right, the main takeaway is that every cyclic group is isomorphic to either Z or Zn. So we can classify all cyclic groups regardless of their order in this theorem. All right. Thank you for your time. I'll see you guys back in the office in just a little bit for a little more on cyclic groups.